Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 21, part 1 on the topic heat load components. So, in this lecture and in the next lecture, that is part 2 of lecture number 21, we will be discussing about the components of heat load. What are the various components of the heat load that will be considered while designing the cold room facility. The different components of heat load, in some textbook they use the term cooling load, both are same only. First is the transmission load, product load, infiltration load, ventilation load, occupancy load, load due to the lighting, and equipment load. So let us see each load one by one, and I will be solving simple numerical question based on the most of the loads which we are considering while we are designing the cold room. Transmission load. So this is the basic equation. The basic equation which is used is UA delta T, where Q is the overall heat gain. This T suffix T refers to the transmission. Your transmission load is QT, U into A into delta T, where U is the overall heat transfer coefficient in watt per meter square Kelvin or degree centigrade. A is the external area of the cold room consisting of 4 walls, ceiling and floor. So this is the load which is due to the heat transfer through the walls on the sides, that is on the 4 sides, through the ceiling or the roof, and also through the floor, that is on all the 4 sides plus ceiling and floor. And delta T is the temperature difference between the outside air and the temperature of the cold room, outside air and cold room. So this is a basic equation which is used, and this how to determine the overall heat transfer coefficient. That is the reciprocal of U, that is the reciprocal of total resistance. Total resistance, that is due to conduction, convection and radiation. Normally in the calculations, the effect due to the radiation effects are negligible. So the heat transfer due to conduction and convection is considered while calculating the total resistance. Once we know the total resistance, 1 by total resistance will give the value of U. So U equal to 1 by. So here this is the summation of different heat transfer quantities. That is the 1 by HI is the heat transfer due to convection on the inner side. 1 by H0 is the heat transfer due to convection on the outer surface or the outer side. And here I have taken 3 layers with 3 different types of insulating material of thermal conductivity K1, K2 and K3, and the thickness of the material are X1, X2 and X3. So let me write this term and explain. So the basic equation is Q equal to U into A into delta T. Q equal to U into A into delta T, where U is equal to 1 by total resistance. 1 by total resistance. And to find the total resistance, R total is equal to, suppose if you are having 3 layers, Suppose we are having 3 layers. This is the thickness of the layer number 1, x1, x2, x3. These 3 layers are made up of thermal conductivity of material whose thermal conductivity of K1, K2, K3. If you see this one, K is the thermal conductivity of the material in watt per meter Kelvin. X is the thickness of the material used in wall layers. So here X refers to the thickness of the layer or thickness of the wall in meter. K is the thermal conductivity. Thermal conductivity. And this is the on the inner side heat transfer coefficient due to convection, and on the outer side, let us take this is the heat transfer coefficient H naught on the outer side. So the heat will be flowing like this. Let me draw it here. So it will be like this. Okay, so this is the direction of heat flow. Let me write this K2 here. So in some book they will use HA and HB, where HA and HB are the heat transfer coefficient due to convection on the inner side as well as on the outer side. So I have used the subscript I for inner and O for outer. So in this case, how to find the total resistance? So there are 2 convection terms and 3 conduction. This is conduction, heat transfer due to from this portion to this portion it is conduction. Again from this portion to this portion it is conduction, and from this portion to this portion it is again conduction. So let us take this is 1, this is 2, 3, and this intersection point is 4. So from 1 to 2, 2 to 3, 3 to 4, it is conduction. So first I will write the resistance for convection on the inner side, that is 1 by Hi plus thickness. If you take the layer 1 or the wall 1, thickness is x1, thermal conductivity is K1. Okay, so that's what I have written here. X1 by K1. X1 by K1. This is conduction. Plus for the second layer, that is between 2 and 3, X2 by K2. The thickness of the different layers or the different walls could be same, and also the same, if same material is used, then K1 equal to K2 will be equal to K3. So this is for the second layer, and from 3 to 4, that is conduction, X3 divided by K3. Then the heat transfer coefficient on the outer surface, that is 1 by H naught. So these 3 are conduction. These 3 terms are due to conduction, and this one convection heat transfer. So that is what I have explained here. So U equal to R, 1 by R total is this one. In most of the refrigeration industry or the cold room industries, it is the calculations are done based on this, like thumb rule, U equal to K by X. Directly U equal to K by X. So generally for panels, for panels, U is equal to K by X. That is, it is like only this portion, 1 by R equal to like X by K. So if you take 1 by R, it will be the reciprocal, which will be K by X. K by X. So if you know the thermal conductivity of the material which is used, the insulation material or any material, and its thickness, then we can find out the heat transfer coefficient, overall heat transfer coefficient. That is what is mentioned here, U equal to K by X. R is the resistance offered by each element, HA, H0, conductive heat transfer coefficient on the inner and outer surface of the wall respectively. Unit is watt per meter square degree centigrade. U is the overall heat transfer coefficient, which takes into account the heat transfer coefficient due to, the heat transfer due to conduction, convection, as well as radiation. But the radiation heat transfer is considered to be negligible. So that's why in the equation we have got conduction term and convection term. Let us move to the next type of load, that is the product load. Two types of products are there. One is live products, another one is dead product. When we are dealing with live products, like for example fruits and vegetables, two types of loads are there. One is sensible heat load, another one is respiration load. So even after the fruits and vegetables, after it has been removed from the trees or whatever, from the farm, it will have some respiration. That will contribute to the respiration load. Whereas dead products such as fish, meat, chicken, etc., in these type of products, the contribution is only due to sensible heat load. Sensible heat load. So live products have both sensible and respiration. Sensible and respiration load. Again, non-frozen products, sensible load. When it comes to frozen products, if a product is there which is not non-frozen type, only sensible load will be there. There is no latent load. Whereas if you take a frozen product, both sensible load will be there as well as latent load will be there. Again, if you take the sensible load, sensible heat load, so that is the load due to sensible heat above freezing, then latent heat load, then sensible heat load below freezing. So above freezing is there, below freezing is. So when we are calculating the product load, we need to calculate, if it is a frozen type of product, we need to calculate the sensible heat load above freezing, above the freezing point of that particular product, then the latent heat load. Then we need to calculate the sensible heat load below the freezing point of that particular product. Components of product cooling load. Pre-cooling. The product temperature is more than the cold room temperature but less than the ambient condition. So this is what I was explaining in the previous lecture. I think lecture number 20, part 1, like pre-cooling. So this process is employed right from the time of the harvest itself. Like it is the removal of heat at the field itself, not at the time of the arrival of the product into the cold room. So if there is a delay, suppose if the ambient temperature is 35 degrees centigrade at the field, if there is a delay in the pre-cooling, in employing pre-cooling by 1 hour, then the shelf life of the product gets reduced approximately by 1 day or up to 20 hours. So when we are having the pre-cooling, the temperature will be less than the ambient. Suppose if the ambient temperature is 35, it will be less than 35, but it will not be less than the cold room temperature. Obviously, it will be more than the cold room temperature. Next one is the loading period, the time at which the product is loaded into the cold room. Cooling load is highest during this period due to warmer product, movement of people and machinery, air infiltration and lighting. So the cooling load is highest during this period, loading period. This is due to the movement of the people, movement of the products or the goods entering into the cold room. When the doors are opened, even when the door is closed, immediately after the product is entered into the cold room, during that interval, there will be leakage of air. That is called the infiltration. Load due to infiltration, leakage of air through the gaps or through the holes, etc. And the lighting will be there. So the lighting load also will be adding to the total cooling load. And if there is a machinery, that will be it will be using some motors. So the equipment load also will come into picture. So the cooling load is maximum, especially during the loading period. Cool down period, this refers to the period when the product is allowed to cool until the desired temperature is reached. Product is allowed to cool until the desired temperature is reached. Then there is another term that is called holding period, the time up to which the product is taken out to the market. So that is the duration between the product which is entering the cold room, that is after the pull down period, after it is stored at a particular temperature, until it is delivered to the market or to the end user. Normally the product, here I would like to give one insight, the product loading rate is 4 to 5% of the cold room storage capacity. This is also like a standard, industry standard or a thumb rule which is followed. The percentage of product loading should not exceed 4 to 5%. 4 to 5% of the total cold room storage capacity, of the total capacity. Suppose if there are 3 or 4 rooms are there, if the product 100 kg of a particular product need to be loaded, so it can be, or let us take 1000 kg, 1 ton to be this loaded. It has to be distributed in 4 rooms. If the cold store contains 4 rooms, it should be evenly distributed. So, and distribute the product evenly in all the rooms. So, product loading rate this is very, very important, of the total cold room storage capacity. Sensible heat above freezing. So, let us see the formulas which are used for the product load. Sensible heat above freezing. So, here that I am taking as Q1. Sensible heat above freezing. There are 3 components. One is sensible heat above freezing. That is Q1. Next one is the latent heat. Latent heat load, that is Q2. And the sensible heat below freezing. So that is Q3. So let us see the formula for calculating the sensible load above freezing. So this is the formula. Q1 equal to the basic formula is MCP delta T, T1 minus TC by 3600 into T plus. This is here M. This is not mass load. This is mass. So there is no requirement of M dot. It is M. MP mass of the product into CP of the product into delta T. This one. So where M is the mass of the product brought into the cold room per day in kg. M is the mass of the product, and MP is the mass of the packing material. Since product and packing starts with the letter P, so to differentiate the masses, M refers to the mass of the product or the commodity which need to be stored, and M suffix P refers to the mass of the packaging material. So this is packaging material. Packaging material. Cp is the specific heat of the product above freezing, and CPP, this is the specific heat of the packing material. Packing material. T1 is the initial temperature of the product above freezing. Tc is the temperature of the cold room, and small t is the time period for product cooling in R. So this is the formula. Using this formula, we can calculate the product, the sensible heat, the sensible heat above freezing, which is contributing, which is one of the component of the product load. If the products are stored in bulk, if the product is stored in bulk, then the peak packing heat load, the heat load due to the packaging material or packing material is not considered. So in that case, this term will not be there, the second term will not be there. So it will be MCP T1 minus TC, TF, MCP T1 minus TF, where M is the mass of the product, Cp is the specific capacity of the product above freezing, T1 is the temperature of the product before bringing into the cold room, that is the initial temperature of the product, and TF is the freezing temperature of the product. So using this formula, you can calculate the sensible heat load above freezing. So that is this formula. Latent heat of fusion, that is M into the latent heat, that is the latent heat in kilojoule per kg. The product of M into H, then that will be Q2, that will be Q2. Then the sensible heat below freezing, MCP, from the freezing point till the final temperature, If you take here, this is above freezing, temperature is TF, and freezing temperature is TF, above freezing is T1, below freezing is T2. So this is above freezing, and this is below freezing. This is below freezing. So from T1 to TF, delta T, that is the freezing. The delta T is above freezing is T1 to T1 minus TF, and for below freezing, the delta T is TF from TF to T2. So this is the delta T. So this is the delta T, and here this is the delta T below freezing. So that is MCP delta T. So this also we can find out. And there is one more load. Suppose if it is this one, respiration load, live product. What is a live product? Respiration load, that is Q4. So mass of the product multiplied by the rate of respiration, that is in kilojoule per kg. So when we add Q1 plus Q2 plus Q3 plus Q4, that is the sensible heat load, summation of heat load above freezing, then latent heat load plus sensible heat load below freezing plus respiration load, that will give the total product load. So QP is equal to Q1 plus Q2 plus Q3 plus Q4. So here, just to summarize, the sensible heat load due to freezing, if the product is arriving in bulk, so Q1 is equal to M into Cp into initial temperature minus TF. This is the formula. and here latent heat is Q2 is equal to mass of the product into the latent heat. Sensible heat below freezing is Q3, mass of the product into Cp of the product. There are two specific capacity value. One is above freezing and another one is below freezing. Cp of the Cp specific capacity of the product below. Here Cp value refers to the product Cp above freezing, and here it is below freezing, into delta T. Delta T is Tf from freezing temperature to the final temperature. And respiration load is Q4 is equal to M into the respiration rate. Respiration rate. So this is in kilojoule per. So I will stop this lecture at this point. We will be continuing in the next lecture. That is lecture number 21, part 2. Thank you.